Hey there, and welcome to your next lesson on foundation level mathematics. So we're continuing with numbers now, but we're looking at approximations this time. So we've worked with, calculating things exactly. Now we're looking at how we can perhaps approximate the answer to something, and why would we want to do that over working out something exactly? So that's what we're going to be doing today. So we've just got three sections to look at today. First of all, rounding. How what does it mean to round a number and how do we do it? Next is then estimation. So we're using rounding to then estimate something. And like I said, we'll look at why exactly would we want to estimate? Well, why would we not just calculate something exactly? And then finally, we look at the error bounds of those estimations. So if we estimate something, we're not getting the exact value, we're slightly off from the real value, and that's what's known as an error bound. We're going to look into how we can kind of approximate those and try and keep that to a minimum. We want those errors to be small in our approximations. So first of all, we're looking at rounding. So rounding is like a way of simplifying. We can use rounding essentially to simplify complex calculations. Whether it's be on paper or mental math, it makes numbers easier to read. So if we're presenting some numbers that we've calculated, rather than having to say many decimal places, we can make it shorter, and so it's easier to just see and understand and compare with other numbers, and avoid being overly precise. So certainly, if we're then using those numbers in further calculations, there's no need making things more complicated for ourselves, having something to like say 10 decimal places when maybe we only need 2 decimal places. And we'll look into what exactly that is in a second. So we're here is a number line we have. So let's take a look at some numbers. So we've got, say, 12.3, which would be about here on the number line. And we want to see how would we round that to the nearest whole number. And you can see either side of that arrow, we've got the numbers 12 and 13. There are two whole numbers either side. So when we're rounding, we're going to be rounding to one of those two. But we want to round to the closest one. So in this case, you can see that would be 12. And so that's what we're doing when we're rounding to some specific type of value. Like in this case, the nearest whole number. And we basically want to move to then the closest whole number. So another example would be something like 10.8 here. You can see the whole numbers are 10 or 11. What is the closest one? That one's 11 here. And finally, say 12.5 is a particular case where you see it's directly in the middle between two whole numbers. It's like, okay, which way would it go? Because it's equal distance away from 12 and 13. And in this case, it's our general practice that it rounds up. This is more just a mathematical convention that we agree to, so that everyone's rounding in the same way essentially. So say if we're trying to do a calculation, so like 12.3 times 10.8, for example, we could simplify that calculation by rounding each to 12 and 11. So we get 12 times 11 is 132. If we compare that to the actual value, which would be 12.3 times 10.8, gets 132.84. You can see we're pretty close. Like the error is just 0.84, but 12 times 11 would be much easier to calculate. So that's one example of using rounding to simplify a calculation. Right, so now rounding, it doesn't always have to be to the nearest whole number. Let's look at a case here where we're looking at rounding to the nearest 500. So you could imagine this being like the profits that a company makes or something, and you're presenting it to then your boss or something like that. And they don't need the exact, like down to the nearest pound or the nearest penny. They just need to the nearest 500, just something like that. That would be an example of doing this. So say if we had this number and we want to the nearest 500. Well, again, if we have a number line like this, which you can always write a number line if it helps you understand this. But with practice, you won't need a number line. So you see it's there, and you see the two multiples of 500 that we have either side of it is going to be 6,000 and 6,500. And on that number line there, you can see that 6,500 is the closest one. So if we're rounding to the nearest 500, that's going to be 6,500. If we look at this case, so you can see it's kind of in the middle on the number line. Like from the number line itself, you might not be able to tell, but looking at the actual number itself, it would actually round up to 8,000. And the reason why that is because you see between 7,500 and 8,000, the midpoint is 7,750. And this one being 7,752, it's just slightly above that midpoint. And so that means it's going to be a little bit closer to 8,000 than it is 7,500. So that does indeed round up. So one last example would be 7,590. And this one's a lot more straightforward. You can see that's definitely going to round down to 7,500 because it's quite close, much closer than it is to 8,000. So that's an example of rounding to the nearest 500 or to the nearest any number, really. It might be to the nearest 100, nearest 50, nearest whatever. And it's going to work in very much the same way. So now if we look at actual decimal places, which is what you're going to encounter quite often, probably most often, really. And say if we had a number like this, and this would be an example of like that third bullet point I've got there, where you might have a number that is overly precise. Like this one, we've got many decimal places, and perhaps we only need 2 decimal places. So on this number line, that number is roughly about here. And say if we want to get to the nearest 2 decimal places, and you can see on that number line, that's either 1.05 or 1.06. And you can see it would be closer to 1.06. But say if we had to do that just based on the number we have itself. So you take a look at that number. You can see I've drawn a little red line after the second decimal point because that's where we're rounding. We want to round to 2 decimal places. So that's, in case you're unsure, that's what decimal place means. It's the first decimal place is the first digit after the decimal point. Second decimal place is the second digit, and so on and so forth. So we're going to that second digit. So we draw a line there at the 5, and then we look at the next digit, which is the 6, and you see, is that number greater than or equal to 5, or less than 5? So if it's greater than or equal to 5, then it's going to round up, like what we've seen in some of the examples before. If it's less than 5, then that means it's going to round down. So that number tells us which side it's closest to. So this one, we do see, is going to round up to 1.06. And we can do the same thing with another digit like this, because you see with these very precise digits, the number line is not so useful now. And we need to look at more just at the numbers themselves. And you see 1.08, then the next digit is a 1. So that tells us that this is definitely closer to 1.08 than it is to 1.09. So that's going to round down like that. And one final example, like 1.064999,812. So here we've got another example where it's almost dead in the middle between 2 options. So we've got 1.06 and 1.07 are our 2 options. Is it going down or is it going up? But we can see, because the next digit is 4, I mean, it's 4999, so it's just ever so slightly below the 5. But it is below, and so we can see that's definitely going to round down to 1.06. So you might have some cases like that where it's right on the boundary, but if it's below, it's going to go down. If it's above, then it's going to go up. No questions asked. So, right, that's how that works with rounding. One last thing to deal with is something what's known as significant figures, which is when you're trying to, we tend to use significant figures when we're dealing with something like this, where we've got a really small number, especially a small number that maybe we don't know precisely how small it's going to be. So, how many zeros are we going to have before we actually start getting, non-zero digits? And you see, if we try to round to decimal places like here, 4 decimal places or 7 decimal places, you see it just comes out to 0. 0.0000 is just still just 0. And so what we might use is, say, significant figures. So something like this, which is 2 significant figures. And what that means is all those zeros, what are sometimes known as leading zeros, because they're at the start of the number, those leading zeros, you just skip over all of them, and then you start just counting decimal places from the first non-zero number, which is what's known as your significant figures. The zeros are insignificant. The first from the first non-zero digit are significant figures. So you see 2 significant figures gets 3, 4 like that. But an important thing to be aware of is, say if we had 4 significant figures like this, but you see there's a 0 in there, that 0 is now a significant figure. So the insignificant ones are just those leading zeros. But once you hit the first non-zero digit, you now just start counting decimal places as normal. So we get 3409 is our four significant figures. So yeah, a little thing to be wary of there. So there's our different types of rounding and what their purpose is and why we use them. So let's use them in estimation now. So we've seen one example of this already. Like say if we have this calculation, we could round each of those digits to make this approximately 12 times 13. And that's what that little wavy equal sign means. It means approximately equal to, not exactly. And then we can calculate that. It comes to 156. And we can do the same thing here with an addition. We could round each value individually and then add them. And we get this value. And finally, we could do this multiplication here. Very much the same thing again. If we round each one individually and then calculate it, and we get an answer like that. So here's a bunch of examples of using rounding to estimate. Now let's try and think what kind of estimation we're getting here and what kind of errors are we going to get. So what we can do is look at how we've rounded each value and look at the operation that we're doing between those values. So here we've got a multiplication. That's the operation we're doing. And we've rounded down one value and we've rounded down the other value. Like 12 is rounded down to 12. 12.1 has rounded down to 12. And 13.2 has rounded down to 13. So both of those values are now less than what they actually should be. And then you multiply those two together, the end result we can see is going to be less than what it should be. So this is what's known as an underestimate. So we've underestimated the true value. Like the true value is going to be a bit more than 156. So the error we've made is that we've got a value that's a little bit too small. And you see this addition here, we can kind of do the same thing. We see the 66.7 is rounded up, 45.9 is rounded up, and we're now adding these two together. So if you take two numbers and they've both been made slightly bigger, and then you add them together, the end result is going to be slightly bigger. And so this is what's known as an overestimate. So the value we've got here, 113, is bigger than what the true value should be. And you can always check these calculations and you'll see that is the case. The last case is one like this, where we've got two numbers multiplying each other, where one is rounded up and the other one's rounded down. Now, this is an ambiguous case because, okay, one's rounded up and one's rounded down, and so they're going to cancel each other out to a certain degree, but not exactly necessarily. I mean, they might do, but most of the time they won't. And okay, how much are they going to cancel each other out? Like, is it still going to end up being an overestimate or is it going to be an underestimate? We can't know for sure. So this is like an ambiguous case. You can't really know. So this is something we can't always determine. It just depends on how things have been rounded. So, but it's you got to be very mindful of the operator. So let's look at say a division or subtraction as well. We're going to look at. So here we could do the same thing again, where we approximate by rounding each value, and then we can just simplify that fraction as we normally do. Here we've got a subtraction where I round each value to be 145 minus 21, and we get 124. And then here we could take a more complicated fraction where it's got multiplication on the numerator and denominator, and we can just round each of those values individually, and you'll see you get this answer. So each one we're just rounding to a whole number. And okay, so now let's start considering these and see is it an overestimate or underestimate or whatever. So well, of course, yeah, that final fraction we can simplify the 5/8 first. Right. So that first calculation, you see the numerator we've under estimated, because we've rounded down, and then the denominator we've rounded up. So now you've got to kind of think about it. Like we've got two numbers, one divided by another, and the top one has been made smaller. So that's going to make the overall fraction smaller, wouldn't it? But the denominator has been made bigger. But because it's on the denominator, like you're divided by that number. So dividing by a bigger number is going to make the overall fraction smaller. And so both of these roundings have made the fraction smaller. And so we can be sure that this is an underestimate. That 4/5 is an underestimate of this value. It's not, the true value will be slightly bigger. Similarly, with this subtraction, you see we've made the 144.5 slightly bigger through rounding, and the 21.3 has been made slightly smaller through rounding. And so, okay, you've got a number which we've made slightly bigger, and now we're subtracting a number that's been made slightly smaller. So, because we're subtracting a slightly smaller number, that's going to make the overall value bigger because you're subtracting less. You're subtracting less from the first value, and so both of these make the overall calculation bigger, and so this is going to be an overestimate. The true value will be slightly less. And then finally, with this bigger one, you can see on the numerator they're both round. Both those values are rounding down, so that multiplication is going to be smaller than it should be, as we've seen before. Similarly, on the bottom, they're both rounding down, so we know that value is going to be smaller. But in terms of the overall fraction, the numerator has been made smaller, so that's going to make the overall fraction smaller. The denominator has been made smaller, so now we're dividing by a smaller number. That makes the overall fraction bigger. And so you've got one set of rounding is making the fraction smaller, another set of rounding is making the fraction bigger. That's going to be an ambiguous case because we don't know how are those going to cancel out. It all depends on how much you've rounded by. Is the underestimation going to outweigh the overestimation or vice versa? So that's a thing you have to be wary of. That there's not always a clear answer with these sort of things. Right. So that brings us to our final section on error bounds. So we kind of categorize our solutions into underestimates or overestimates, which then tells us whether that our error bounds, like our error, have we made an error being slightly too big or slightly too small. We're going to build on that idea now. So let's take an example here of like a football pitch, and we've got dimensions of a football pitch like this. However, actually no, I'll come back to that in a sec. Let's calculate the area. So using these dimensions, we can get the area just like this. So we haven't done much on calculating areas, but the area of a rectangle is just simply going to be the two side lengths multiplied each other. So we get 11,500 meters squared. But say if we now learn that these two distances were rounded to the nearest meter, and what we're trying to do here, we're trying to calculate, like we need to, I don't know, for example, say if we need to buy seed to grow grass on this field, we need to regrass it, and we need to get an accurate measurement of how much area this is. Because of this rounding, there's going to be an error bound associated with that area. And okay, we want to try and work out what that error bound is. So let's look at, say, the lengths first. If this length, the 125 meters, has been rounded to the nearest meter, that means the true length is going to be this, 125 plus or minus half a meter. Because you think about it, another way to put it is like this, like as like an interval where any value between 124.5 and 125.5 is possible. Because you think about it, any value within that range would round to 125. If it was slightly below 124.5, then it would round down to 124, wouldn't it? Or if it was slightly higher than 125.5, it would round up to 126. I mean, 125.5 would technically round up to 126. So it's like we're saying up to 124.5, but not including that. But you don't have to be that specific. But you see, that's the range of values that would round to 125. So that's all the possible values it could have been. And we can do a similar thing with the width, because the width was also rounded to the nearest meter. So we've got 92 plus or minus half a meter, or you could express it like this interval, whatever works best for you. Between 91.5 and 92.5 are the values that will round to 92 meters. So if we wanted to then calculate our error bounds for the area, So first of all, we could calculate what is the minimum the area could actually be. And how we would do that is by taking the minimum value of the length and the width, because we're multiplying here, aren't we, to calculate area. So if we take the smallest possible value the width could be and the smallest possible value the length could be, we multiply them together and it will get us the smallest possible value the area could be. And that would get us this. And then we can kind of do the same thing to find the maximum value. So we take the maximum length the width could be and the maximum length that the the width could be, and multiply those two together, and it's going to get us the maximum the area could possibly be. And so now we get this interval essentially for the area. So we got the value of 11,500, but that, due to the rounding that's gone on, we can see that the true value could be anywhere within that range. So say if we wanted to ensure that we have enough seed to grass this entire pitch, we could do we could make sure we buy enough for that maximum value of 11,608. And that's how we could then be definitely sure we've got the right amount. So yeah, that's an example of error bounds there. And you see, it's quite significant. Just rounding to the nearest meter there, in terms of the area, the area could be off as much as 100, like over 100 meters squared. So that these roundings can be very significant. Right, so let's look at one last case. And that's, say, imagine you had like a player who runs the pitch. They run the full length of the pitch like this, and they do that in 15.4 seconds. And that's where it's measured. And you calculate the speed that player was running, and it was 125 meters, or the average speed essentially, 125 meters. So the distance divided by the time it took them to run that distance will get us their speed of 8.12 meters per second. Now, say if the record for players on their team, the record, like average speed they've done, is 8.1534, and this was done at some events, say, where they had a greater accuracy. Look, this has been measured to 4 decimal places as opposed to only 2. And this player was saying actually they potentially could have been running faster than this person, but maybe it's come out lower due to rounding. And we want to think, okay, is that possible? Could they possibly be right? Well, we can do a similar thing like what we did before. So, okay, let's consider the lengths first, which will be the same as before. The length of that pitch will be 125 meters plus or minus half a meter because it's been rounded to nearest meter. Similarly, with the time they did, we've got 15.4 plus or minus 0.05 seconds. So, because that's been rounded to the nearest, 0.1 of a second. And so, you can see 15.35 to 15.45 are the values that would round to 15.4 if we're rounded to the nearest decimal place, like 1 decimal place. So, right, and so now we want to consider, is it possible that he could have been running faster? So let's look at like his speed error bound. So what is like the minimum speed he could have been going? How we would do that is if we take the lower bound of the distance divided by the upper bound of the time. So remember like what we've seen before. So if we're essentially rounding the distance down and we're rounding the time taken up, so the numerator is being made smaller, the denominator is being made bigger. Both of those are going to have the result of making the overall fraction smaller. So we can see this is going to be a lower bound, sorry. So that's the important thing to be aware of there, that when it comes to a division or a subtraction, it's not just going to be the same. You see, one of them we're rounded down, the denominator we're rounding up, and that gets us the minimum value. And then vice versa, if we wanted to find the maximum value, okay, well, that's going to be when we take the maximum possible value for distance, which is the numerator, and the minimum possible value for the time. So it's like you've run more distance in less time. It makes sense that you're going to be running faster. So, but you can see mathematically that it's going to make the overall value bigger. So we can see that's going to be the maximum possible speed it could have run. And so if we look at that, you see his actual speed could have been anywhere between 8.06 and 8.18. Therefore, there is some validity to what this player is saying. He possibly could have been running faster. He could have been running as fast as 8.18, which would be faster than the record there. It's only a small chance, but it is possible. So this is an example of, error bounds, and we need to be aware of those error bounds and how they affect our calculations. Um, are they making it bigger, smaller? And here we're sort of calculating by how much. So that's it. It's a relatively small topic of approximation. So we're done there for today. So I'll leave you with this. Did you know that even extremely accurate measurements can lead to very large error bounds over time? One example of that would be something like the weather forecast. Like you've probably seen this where you look at the weather forecast, but it's never accurate for any more than a few days at a time. And the reason why that is because no matter how accurately we measure the weather today, when you start predicting further and further into the future, very, very small errors can grow over time. Um, and this is a, there are plenty of cases where this can happen, and this whole field of mathematics is what's known as chaos theory. It has small errors grow into big errors over time. Um, yeah, like I said, like one example is the study of the weather, which is what's known as meteorology. And here's like a sort of visual way of seeing it. Like you can see small errors that just stay very small over time, but then gradually they can grow and become very large. And that's what can limit sometimes calculations when we're trying to predict into the future. Uh, but yeah, so there's a fun fact of how this is used in the real world. Here are your takeaways for today's lesson. And I will see you in the next lesson.